Okay, I'll be talking about intrinsically disordered proteins, and so let me start with what these proteins are. So proteins are basically, in a physicist point of view, are biomolecules, biopolymers composed of this blocking unit blocks of amino acids. And these amino acids can differ in charge or hydrophobicity, or they have different side chains, so they have different sterical property. And these kind of 20 alphabets or 20 amino acids, they form all the words or all the proteins that we have in our body. There can be peptides, there can be proteins, and these proteins, depending on the sequences of these amino acids, can also form different geometric structures that are called secondary structures. There can be also sequences like these, where the sequences will lead to no permanent structures. So these are called intrinsically disordered proteins. Now, almost 50% of the human proteins are either completely disordered or part of the proteins are disordered. And this aggregation of this, I'll not talk about aggregation today, but aggregation of this IDPs, they are implicated in different terminal diseases, and the aggregation is kind of regulated by single chain fluctuations. So the protein that we work with is beta casein in water. It's an abundantly available protein, it's found in milk. And it also lacks a kind of a stable 3D structure like a well-folded proteins, and it exists in an ensemble of conformations like all other intrinsically disordered proteins. I'm not going into the detail of the different force field parameters or different interactions that we deal with, but it has 209 residues, so you can think of 209 amino acid kind of placed in after one after other. And the system is we put this atomistic model of beta casein in a box of water. We put some counter ion so that it's neutral, electrically neutral, and we follow the conformations and the dynamics of these intrinsically disordered proteins. Just to give you an overview of what kind of structures or what kind of decoration of this amino acids this beta casein has, it has this, so usually in protein community, we start from this NH2, it's called N-terminal. It has 40 charged residues, which which wiggles like a hydrophilic part, and then it has a moderately hydrophobic part and the hydrophobic part. But it's a very, very gross overview of it. I will talk more about what we actually find in our atomistic simulations. Right. So these protein conformations often are stuck in different local minima. So to avoid or to circumvent this local minima, we follow this kind of different enhanced sampling methods. So I will not go into the details because of the brevity of time, but what the essential message is that we can access the conformation of really high temperature, where the barriers for different local minima is really low, and we can access that at lower temperature, which is the lowest rank temperature. Right. So if we do that, what we find is that this kind of a free energy landscape that we plot on this radius of gyration versus solvent access, is the exposure of the protein to the solvent. And this RG gives you an estimate of the overall size of the protein like this. And this gives you an estimate of how much the protein amino acids are exposed to the solvent. So as you can see, there is one global minima and two local minima. Maybe you can see it better if I kind of show you the all-round visual. So it has a local minima and one global minima and two local minima. But usually in experiments, what is done is they characterize these IDP conformations with often a single RG or often a single Flory exponent or so on, which comes from the polymers. So we asked the question whether this kind of a single average exponent viewpoint is suitable or not. So we have already seen that if we plot it on plot the distribution of RG, there are these three RGs that we can clearly separate. And what we do is that we already can see that one characteristic RG is not enough, and we need to actually look into different funnels to characterize the IDP conformation for this kind of proteins. Right. So, so what we do is that we look into different funnels, we choose the conformations, and then we look at their structural and dynamic properties. So coming to the, we can also look at their shapes, and as you can see that if we look at the conformation in the global funnel, we see the conformations are more close to the spherically symmetric case, which is defined by, which is characterized, quantified by something like asphericity. Whether if we go to the furthest local funnel, we see kind of a random walk like asphericity. We can also quantify something like a Flory exponent, which is often used in polymer physics. So it's basically the one, in this one calculates the internal distances between these monomers, or this Dij between the monomer I and J, and basically plots it as a function of the chain separation. And now if the chains, if the scaling is, one gets something scaling like this, and if the scaling exponent gives you an value of 3/5, it's something like a self-avoiding walk. And if it's 1/3, then you expect a globule-like conformation. What we find is that if we look into the conformations in the global minima, we actually have these conformations that show the scaling of 1/3, that corresponds to a globule. And if we look into the conformations that are this furthest to the in the free energy, we find kind of self-avoiding walk-like behavior. We can also look at the dynamics in these different funnels. So what we do is that we start our simulations, our NVT simulations, starting from different initial configurations in this funnel, and we take these pieces of trajectory and calculate the diffusion coefficient, both the translational diffusion coefficient and the rotational diffusion coefficient. And what's really nice to see is that they actually behave as these different particles moving in at different times. So we actually see this hydrodynamic radius, its hydrodynamic ratio, different for these different funnels. We also looked at the conformational fluctuations of the internal fluctuations of the IDP with the viewpoint of this Raus model, where one actually solves the equation for each of the bead of the polymer, mapping this protein into a simple polymer where there is no volume exclusion. There is no interaction among the residues, but still it works as a fascinatingly beautiful model for the experiments and also simulation. So what is expected is that if it's a coil-like structure, then you will get this different modes that relaxes. You will get a profile which will follow this kind of a behavior. We see that we don't find this kind of a fast decay, rather for different funnels. I'm sorry, I'll just take 30 seconds. For these different funnels, we have different internal fluctuations. So once again, what we see is that we cannot just blindly take the average over all the conformations. We really need to look at the different conformations, and then we can actually characterize this IDP well. So that was our work, and I would like to acknowledge my collaborators and also the funding agencies. And before I thank you, I just want to tell you the take-home message is that if you have an IDP with different minima, or global minima, different multiple local minima, you really cannot take the average of all the conformations. You have to take into account the diversity in this different funnels, and that can only be the right way to characterize these IDP conformations. Thank you.
How many local minima are there?
So in
Like
this,
if I take a sequence of length L, proteins amino acid sequence, so is it like 4 to the power L will be the total number of sequences?
no.
So how many global minimum are there? Local minimum.
It's not possible to predict that. I mean, you can predict the conformation, say RG, average RG, something like that. There is predictive model for that, but you cannot really predict how many global minima are there for
This
the.
what I mean is it like
sequence.
order 1 or some scaling of the length of the
there is actually complicated relations that involve charge decoration, that involves the hydrophobicity. I mean, it basically depends on the decoration of the amino acids in the sequence. That's the key determining factor. But once again, you cannot. You have to look into simulations.
I think what's interesting is that it's about order one, right? or 10 or something, the kind of conformations it can fold into different kind of structures where you still see for a protein structure. Those are the minimum.
It's not folding actually. So you have a rugged in a free energy landscape. So you hop from one minima to another minima.
How many minima are there?
It's of the order of one or maybe,
That means
yeah.
if I make a long protein sequence, it remains, that's what we.
Yes,
order,
yes,
right?
yes.
So just a few of them.
Yes, it's few of them, yes.
Can you go back to the slide where you were showing this exponent here? Yeah. So here, I think you mentioned in the global minima, you get the globular structure.
Yes,
And this 350 is for the local minimum, I did not get that.
yes. So if you, so this one is for this kind of structures.
Yeah, but
This is for the local minima. This is for the local, yes, one of the local minima, which has the largest RG on average. Yeah.
and what about the in-between curve?
So this is, I don't talk about it because it's always intermediate in all the characteristics, it's always intermediate. Since I didn't have time, so this one is RG about on average 2 nanometer. This is around 3 nanometer. This is around 4 nanometers. So in all the characteristics, this is always in between these two. Yes, kind of local, 3 local.
And why does it suddenly, maybe it's a stupid question, why does it drop?
It's simply from statistical point of view, finite size effect. That's all.
So, as I understand, IDPs, they keep moving between their different conformations all throughout time, right? So, like technically, how did you fix it in one state and then probe its dynamics, for example? Because if you just let it evolve, it would just evolve into another state.
Yeah, so if you have RG, so if you have a distribution like this,
Sure.
then it can hop it from here to here to here continuously, right? But if you have a RG which is not like this, but if you have something like there is a barrier, then it can actually trap the conformation for times longer than its relaxation time. So then you need to consider it. So that's my point actually. It's not here.
So the question is about your RG versus SASA plot, solvent accessible surface area, right? It looks very much like folding funnel, right?
Yes.
Where you plot against the reaction coordinate, right?
Yes.
So question is, I mean, how you are doing the calculation for, because these are the output parameters, RG and SASA are output parameters, you cannot fix them.
Right.
So how you are making this plot?
So I just took the conformations from this replica exchange simulations and I checked their RG and SASA. So I worked with other variables as well, just to see that who give, I mean, what set of parameters will, observables will give me the largest number of local minima. So that's the thing that I did.
Okay, so let's thanks the speaker.